Hello, everyone. Good morning, good evening, good afternoon. I'm Kannan Muthukkaruppan, co-founder at Yugabyte, and my pleasure to welcome you all to today's episode of YugabyteDB Friday Tech Talk. And today's speaker is going to be Premkumar Thangamani. So welcome, Prem. Would be great if you start off with an introduction, and then I'm excited about the topic about scaling. So please go ahead.
Thanks, Kannan. Hey, folks, I'm Premkumar, technical evangelist at Yugabyte. Today, we'll be talking about scaling your applications on top of YugabyteDB. So this will be an interactive session. So please ask questions in the chat and they'll be answered by our team. Let's first go over the list of topics that we'll be going to look at today. So we'll delve into the interesting topic of scaling, which is vital for today's modern cloud-native applications. We'll explore why scaling is necessary in the first place and look at the various strategies for scaling. So YugabyteDB is known for its scalability, but it does not happen magically. We'll look into the internals of YugabyteDB architecture and understand why YugabyteDB is an excellent choice for a scalable database. We'll also understand the various dimensions of scalability like reads, writes, and transactions, and see how well YugabyteDB scales these dimensions. So before we go into all these topics, we need to understand why we have to scale. So you have an app, probably your app has become very successful. Users love your app. You might want to handle seasonal spikes like Black Friday or Cyber Monday events, holiday traffic basically. Or you might have to do huge streaming events like Super Bowl or World Cup events. You might have to handle massive workloads, high throughput workloads, or workloads like IoT or audit data, which are ever-growing datasets. So to handle these things, you can have to scale your cluster. Let's see what types of scaling options you have. So to handle high throughput or large data sets, you can choose between two types of scaling, vertical and horizontal. So these are very standard terminologies. Vertical scaling, also known as scale up, means you increase the resources of your nodes. This is about getting more CPUs, multiple disks, or increasing the memory on the machines. You can do this for both traditional and distributed SQL databases. But for single node databases like MySQL, Postgres, Oracle, this is practically the only choice. The primary problem with this scheme is that it's very disruptive and it cannot scale beyond a certain point. On the other hand, horizontal scaling, also known as scale out, means adding more nodes of the same type as your existing cluster. This is the strength of a distributed database like YugabyteDB. So this is less disruptive. Only some data has to move in horizontal scaling. You can add more machines as and when needed. There is literally no limit. When using YugabyteDB, you can do both these types of scalings, vertical and horizontal. However, for YugabyteDB, horizontal scalability has been a first-class feature from day one. Let's see how YugabyteDB scales. So horizontal scalability requires transparent sharding of data. That is basically the movement of data from one machine to another. So let's see how this happens without service interruption. So all the table data is split and stored in what we call tablets. The term tablet should not be confused with modern usage like iPad or Microsoft Surface. It's just that ancient humans stored literature and content on sets of flat wooden and clay slabs known as tablets. Some call these tablets as shards. So each row in a table is mapped to a specific tablet based on the primary key of the row. In cases where you don't have the primary key in a table, we automatically insert something called row ID, and that is used for mapping. The mapping of a row to a tablet is deterministic, so we can exactly locate on which tablet a row resides. So this process, we call it auto-sharding. Tablets are also replicated by follower tablets via raft for high availability. Although the tablet is responsible for reads and writes, the followers have a copy of the data too. Raft ensures that data consistency on failures. In an RF3 system, there is one leader and two followers. So we are going to use the same this illustration for the slides. Let me explain the layout here. So this is your app. This is a 3-node cluster with 3 nodes. This is the table. We'll see how the table grows and how the data is distributed. So this notation is for basically to say that, hey, keys T1 and T2 are present in tablets T1. So replication factor 3 implies that there are 3 copies of the data. So this is the tablet leader, T1. The solid circles are leaders, the dotted circles are followers. So there are 3 copies of the same data. Nodes could be in different regions or different zones for resilience. So as I said, for every tablet, there are every tablet leader, there are 2 followers because this is an RF3 system. In an RF5 system, you will have 4 followers. Now let's start adding more rows. So when we add rows 7 and 8, they are written into the same tablet T1. So as you can see, 7 and 8 go into T1. The tablet T1 starts to grow, and so do the followers because the followers get the data replicated. So when a tablet reaches a specific size, the threshold, it splits. This is configurable. For the purpose of this illustration, let's say that the threshold size is 4 rows. In reality, it is in bytes. So as the tablet T1 has reached a threshold size, it prepares to split into 2. So there are other tunable configurations related to this, but we are not going to look into them deeper today. The tablet T1 has now split into 2 parts, T1 and T2. So T1 holds 1 and 2, while T2 holds 7 and 8. So the tablet splitting is very fast and it maintains ordering. Notice that tablet T1 and T2 are located in the same node, node 2. So in reality, although I have shown that T1 has split into T1 and T2, in reality, 2 child tablets are created. So effectively, T1 becomes T3, T4. But for a simpler illustration, we have kept it as T1 and T2. So as the cluster is unbalanced, rebalance kicks in. The tablet leader T2 is moved to node 1. The switching of leaders is very fast. We'll see how we'll look into this a little deeper later. Now, you see 2 nodes in the cluster are active. So here, node 2 and node 1 have tablet leaders, and they both can process queries. Now let's add 4 more rows.
Maybe one point worth mentioning, Prem, on the previous slide is I mean, while it may seem like splitting a tablet could be an expensive operation, because maybe the tablet has 10 gigabytes of data and you want to split it into about 2 child tablets. So it might be, I thought it will worth mentioning why that is a quick operation. So the way YugabyteDB handles that is it's more initially done as a logical split. So 2 child tablets are created, but we don't actually make copies of the data yet. They logically point back to the parent tablet. One child tablet owns logically the one half of the parent tablet and the other one the other half of the parent tablet. And so because it's a logical operation with like ref counting, it happens very quickly. And in the background, then when compactions happen, we decouple the dependency of these child tablets from the parent tablet. But that ends up being more of a background activity. So I thought I'd just share that insight with the audience.
Cool, it's so nice to hear for the people who designed the system. So let's add 4 more rows, 3, 4, 5, 6. Now these get added to different tablets. So 3 and 4 go to T1, and 5 and 6 go to T2. So yeah, now each tablet has 4 rows again. Now, if you see, the cluster has been horizontally scaled. Any operation, inserts, updates, deletes, or selects can now be handled by 2 nodes, as we have shown. So now, as the tablets have reached the threshold size again, each tablet splits again. Right now, we have 2 tablets. Now, when we say the count of tablets, we count only the leaders, not the followers. The 2 tablets, T1 and T2, so T1 and T2, have now further split into T3 and T4. Now you have 4 tablets and respective followers in other nodes for resilience. As you can see, there can be many tablets in the same node. A table can be pre-split during creation for it to be immediately scaled across all the nodes. So this is how YugabyteDB is able to distribute data across multiple nodes. This is what makes YugabyteDB scale. So this was just a very simple example with just 1 table and few rows. In reality, a cluster can have 100 plus tablets. To recap, table node data is stored in what we call tablets. A table is split or sharded into tablets. YugabyteDB supports both range and hash sharding. We are not going to go into details of what is range and hash sharding. Tablets are distributed across nodes. That's how we scale it. During rebalancing, the tablets are moved. The tablets can also be pre-split during creation so that the whole cluster becomes immediately active. Nodes can have many tablets, and tablets are replicated by the followers for high availability via raft. So adding nodes easily to an existing cluster is the foundation of scalability. So we saw how data has been split and moved, but let's see how YugabyteDB handles new nodes added to the cluster seamlessly without any service interruption. So we are going to look at the same cluster that we used before. So in your cluster, you notice that node 3 is taking more traffic because it has two leaders. Now you decide to add a new node to scale your cluster. As node 3 has two tablet leaders, T3 and T4, this is a likely candidate to be moved to the new node. So this is because YugabyteDB will try to keep the number of tablets in each node balanced. But how is this tablet move done without any service disruption? So instead of just moving the tablet leader to the new node, which would cause service disruption, YugabyteDB creates a new follower in T4 in the newly added node. So this new follower bootstraps its data from the leader. So once it's up to date from the leader, a leader election is triggered with a hint to make the follower in node 4, the T4 in node 4, to be made as a new leader. During this entire process, this is completely in the background. During this entire process, you still have the leader T4 active, which will be processing queries, and the throughput of the app is not affected. Now, the follower in node 4 is made the leader, and that node can start taking queries directly. So this switching of leadership takes less than 5 milliseconds. Yes, it's that quick. This immediately relieves the cluster. That's because you have 4 nodes in the cluster active. Previously, you had only 3 nodes. So as the system added a new follower for T4, if you see, this was a new follower added that has become leader, so T4. Now there are 4 copies of T4. T4 here, 1, 2, 3, and 4. So this was an RF3 system. RF3 system means that you have 3 copies of the data with 1 leader and 2 followers. So now the tablet T4 is over-replicated with 4 replicas. Another T4 replica, say the one in node 2, is automatically removed. So this is how efficiently a node is added to the cluster and scaled seamlessly. So not just the leaders are balanced, the followers are also moved across the nodes to keep the data distributed evenly. The same process of bootstrapping is repeated for the followers too. The cluster is continuously monitored and rebalanced as needed. So now the leaders and the followers are balanced across the nodes. All the 4 nodes can process the queries. Now the node addition is complete and your cluster is fully scaled out. So to recap, seamless node addition is the basis of scaling. It's a very simple operation. It's completely transparent to the application. There is no service disruption. Data is moved magically, in fact, automatically and magically, in the process that we call rebalance.
And maybe I would just say, like, so fundamentally, like, you start with a certain number of nodes and maybe hundreds of tablets on those nodes. You added, in your example, you added 1 node, but you could have added 5 nodes, right? So there's an initial state, you're adding a bunch of new nodes, and you have hundreds of tablets on the source. And what Prem explained is, in some rate limited manner, the system in the background works on a few tablets at a time, temporarily increases their replication factor, makes the right decision on which ones to move to the new node in a leader role, which ones to move in a follower role, and sort of makes this happen in the background, right? So the system stays online throughout the time. And as the initial few tablets start arriving on the new nodes, the system already is benefiting from the new nodes. It doesn't have to wait for all the tablets to arrive before the new nodes become useful. Yeah.
Thanks, Kannan. Okay, so now you have added new nodes to the cluster, but how will your application know that new nodes have been added and traffic can be sent to the new nodes? So there are a few ways. Let's look into each of them. So one technique is to hide your entire cluster behind an external load balancer like HA proxy or a network load balancer, NLB. So this way, your applications need not worry about how many nodes are there in your cluster. The application talks to the load balancer, and the load balancer distributes the connections across the nodes. So the problem with this is, it works, but the problem is when you add new nodes, you have to make sure your load balancer configurations are updated. Also, in a multi-region scenario, the load balancer may not have any idea about the topology of your cluster. So you can have your cluster spread across US East, US West, and US East fails. You want to fail over to US West, and the load balancer may not know how to do that. So how do we get around these? So for this purpose, Yugabyte ships a smart driver just to solve these problems. So all you need to provide is just one or few IP or hosts from your cluster, and the smart driver will figure out the entire cluster topology. The smart driver is embedded inside your application, unlike the load balancer. So it avoids an extra hop. So in the case of a load balancer, external load balancer, your app will have to talk to the load balancer, and the load balancer talks to the nodes. But in the case of a smart driver, which is embedded inside your app, there is no additional hop. So also in the case of a multi-region scenario, it will correctly fail over to the other regions in case the primary region fails, as it knows about the topology of your cluster. So using the smart driver for load balancing is minimal effort. It's very easy to configure. In fact, all the configurations are just on the connection string. You don't even need a separate configuration file. The smart driver understands the topology of your cluster, and it supports automatic failovers. So there are a lot of tunable parameters related to smart driver. We are not going to look into them today. You can check out in our docs. Okay, so we have seen why YugabyteDB scales and why Yugabyte scaling is necessary. Now we're going to see the different dimensions of scaling, like reads, writes, and transactions, and how each of them work in YugabyteDB. So reads are very simple and straightforward. It's probably the simplest operation in YugabyteDB. So when an application issues a read request, it's redirected to the leader responsible for the keys in the request. The leader has the latest data and responds immediately. A simple select involves 2 nodes maximum as shown. Followers are not involved. For example, so this is the app issues a request, a select request for k equal to 5 to node 2. It's connected to node 2. And then that request, the system immediately figures that, hey, k equal to 5 is not present in T2 because the row location is very deterministic from the sharding. And it internally redirects that request to T2. And it retrieves a row for k equal to 5 and sends the response back to the app. So this is this internal redirection is completely transparent to the app. So all the nodes in the cluster can process selects concurrently. So each query hits a fixed number of nodes that is completely independent of your cluster size. You can add more nodes in order to scale reads further. So this is a perf that shows how YugabyteDB scales reads horizontally. So we do religious, regular perf testing on our system, almost on a daily basis. The workload is a simple select from 10 tables using Sysbench, a standard DB benchmarking tool. The way we run the test is we keep increasing the workload till the latency crosses 3 milliseconds, and then we stop. So technically, it can handle a lot more requests, but your latency will be high. The cluster consists of 16 core machines with 64 gigabyte memory. We run our perf tests on M6i instances as they give a good balance of CPU and memory. So as you can see, as we increase the number of nodes, 3, 6, 12, the number of reads, maximum number of reads handled within the latency in the cluster also doubles, 125K, 250K, and 500K. So these are 500,000 reads per second on a 12-node cluster. So consistent reads are served from the leaders. Followers are not involved in this path. You can technically read from followers, but that's a completely different paradigm called follower reads. So that your reads may not be consistent, but for consistent reads, you read from leaders. YugabyteDB scales reads linearly, and as shown in the previous graphs. So YugabyteDB excels in point lookups. Point lookups are basically you have a key, and then you look up the value for that particular key. It knows exactly where to look up and then immediately returns. So YugabyteDB excels in that play. The next dimension in scaling that we are going to look into is writes.
Yeah. Maybe one question that was coming in is like we talk about, in your examples, you talk about like scaling from 3 to 4 nodes.
Okay.
But I mean, I understand that it is simpler for illustration purposes, but more likely people are starting with a multi-zone cluster, like a 3-node cluster in 3 different zones.
Yes.
And in fact, even if you look at your performance data, you went from 3 nodes to 6 nodes to 12. So they were kind of like multiples of 3, probably because it was a multi-zone cluster and we were kind of scaling that way. So is there any impact with some of the, the topics versus, if this was in a single zone going from 3 to 4 nodes versus multi-zone 3 to 6, any differences or?
Yeah, but most of our tests are done on a single node because we try to avoid the cross zone latency. But when you increase from you add nodes on your multiple zones, you add that because of resilience, because to support node failure. But you add additional latency because from interzone latency adds about 1 millisecond. So in case you are talking to a node. Sorry, go ahead.
I think fundamentally, I think it's I would say all the concepts you have explained simply naturally extend to the multi-zone case. There isn't any fundamental difference. It's just that the more common addition would be you would take 3 nodes and you would probably initially take it to 6 nodes, right? To scale. And but the mechanics of whatever you described are literally the same. Yes, the latencies are going to be slightly higher instead of like, half millisecond, maybe in interzone latency might be closer to 1 millisecond for round trip and all that. But in terms of how load balancing works or scalability works, the concepts remain very much the same. There might be hundreds of tablets that now have to get spread out among the new nodes that are available, and things happen in the background, a few tablets at a time. We make sure that the tablets are still respecting their, zone aware placement. You don't want to end up with, in the end state, you want all the 3 replicas of a tablet to still be on 3 different zones. So we respect this. Yeah. Cool. Thank you.
So our next dimension is writes. So writes are actually transactions internally, but we have a lot of optimizations for single row mutations. So let's see how they work and how they are scaled. So once you have multiple nodes in your cluster and tablets in them, you can connect to any node in the cluster to operate on any data. So that's the basis of scalability. So this enables your reads and writes to be distributed across all the nodes in your cluster. So when a request is sent to a specific node, it figures out where that particular key is and it internally redirects. So what happens when a write during a write? So when an app does a write, insert, update, or delete, the write is first sent to the leader, and the leader. So it figures out the leader. It's sent to the leader here. So for example, even if you connect to node 2, it's internally redirected to the leader in node 1. Similar thing will happen if the rows are retrievable from the multiple tablets in other nodes. The leader then sends the write to the followers. So this is the leader for k equal to 5. It sends after it takes in the write, it has to replicate the write to its followers. That's because YugabyteDB does raft-based replication and it expects quorum. So this is an RF3 cluster where we say that there are 3 replicas. In an RF3 cluster, at least one other follower should be up to date. So it waits for at least one follower to acknowledge the write. So this is the added latency in writes. In the case of reads, the request directly goes to the leader and then immediately is responded. But in the case of a write, once the leader takes in the write, it has to be replicated to at least one other follower. So let's see how well writes scale. So this is the perf run that shows how YugabyteDB scales writes horizontally. The workload is simple inserts into 10 tables using sysbench, same DB benchmarking tool. The way we run it is, so we keep increasing the workload till the average latency is 10 milliseconds. So in the case of reads, we did up to 3 milliseconds, but in the case of writes, we do 10 milliseconds because it has added latency. So technically, the cluster can handle a lot more writes, but with much higher latency. So as you can see, as we increase the number of nodes, in this case, we double the nodes, the number of writes, maximum writes handled within the latency, required latency, also doubles. So consistent writes are done using a raft. The writes are sent to the leaders, and leaders have the latest data. Leaders replicate these writes to at least both the followers, and at least one of the followers is definitely up to date. So that is primarily for failover high availability. So even though the write protocol is a lot more involved than reads, writes scale linearly in YugabyteDB. So we have seen how reads and writes scale seamlessly when nodes are added. But let's see how multi-node transactions are handled in YugabyteDB. The transactions are a set of SQL statements that are expected to be executed atomically. So it can get very complex depending upon the needs of your business. To get a distributed transaction working correctly across multiple nodes, multiple tablets, various components are involved. But I'm not going to go too deep into this. So in the simplest explanation, the node that the client connects to acts as a transaction manager. Any node can act as a transaction manager. So if the connection is to another node, that node will act as a transaction manager. So that transaction manager, it acquires the necessary logs. It talks to the respective tablets for the keys involved in the operation, acquires necessary logs, and the transaction is committed to the leader and replicated to the respective followers using two-phase commit. So let's see how YugabyteDB scales transactions seamlessly. So this is slightly a different workload because it's a complex workload. So this is a TPCC, Transaction Processing Council benchmark. So it's the gold standard for OLTP benchmark. So OLTP is online transaction processing. Let me give a quick overview of what the benchmark does. So it actually simulates it's a real-world simulation of how a company operates. So it's a mix of complex transactions like new orders, payments, delivery, status, and stock check. This shows that this performance shows that YugabyteDB linearly increases transactions per minute with the increase in the number of nodes. So as we increase from 3, 4, 5, 6, so 26K, it linearly increases. So you might have noticed that, hey, reads were much faster, single throw operations were a little slower, and then but this transaction is slow because it's a very, very complex operation. And in fact, we had to do a lot more optimizations in the product to actually hit these numbers. The distributed transactions are more involved, and yet YugabyteDB scales transactions linearly. You have to remember one thing, index updates are distributed transactions also. That's because even if it's a single row update, if you update a single row in a table, and if that table has an index, that index has to be automatically updated, and that happens as a transaction internally. To provide the asset guarantees, so we make that a transaction internally. So unlike in the case of a NoSQL distributed system, you will have to do transaction logic within the application. In YugabyteDB, you totally avoid that transaction logic in the app because it's completely handled inside the server. We are at the end of the presentation, so final thoughts. So YugabyteDB scales horizontally pretty well. Scaling is a simple, seamless operation. There is literally no service disruption. You can use smart drivers for automatic load balancing and for removing the additional hop compared to the network load balancers. Reads, writes, and transactions scale linearly and horizontally. Thank you. So check out our source code on GitHub. And if you have any further questions, please reach out to us on our public Slack. That's it. Thanks, Kannan. Over to you.
Thank you, Prem, for covering a lot of ground on time. Yeah, it's a fun topic. And thank you, everyone, for joining us for another episode of YugabyteDB Friday Tech Talk. We'll see you again next time. You can follow us on LinkedIn to get updates on when the next talks are. So I don't know, Prem, do we have one? I think we have one more for this year, correct?
Yes, Frank is doing on retries, application retries.
And this is on December 8th,
yes.
Pacific time. Wonderful. Thank you all for joining.